This film is concerned with the effects of high-altitude nuclear explosions on radars, optical sensors, and communications. To understand how nuclear explosions affect such systems, it is first necessary to understand the interaction of explosions with the atmosphere. We will discuss this interaction, or phenomenology, for explosions at very high altitudes in the ionosphere and in the upper atmosphere. We shall not consider the blast and other lethal effects that nuclear explosions produce. The air we breathe consists almost exclusively of gases and are electrically neutral in their ordinary condition. The number of electrons shown here is, of course, symbolic rather than literal. As we progress towards the top of the atmosphere, however, the gases are exposed to powerful X-ray, gamma ray, and ultraviolet radiation from the sun and from cosmic rays. Above about 90 kilometers, radiation increasingly breaks more of the molecular gases into their atomic or single atom state. This dissociation, primarily from the ultraviolet radiation, affects as much as 50% of all molecules at altitudes of about 100 kilometers. The cosmic and particle radiation also causes ionization. Detachment of the single electron leaves the remainder of the atom or the molecule with a positive charge. This can happen to single atoms or to either one of the atoms of a molecular pair. Being electrically charged, free electrons are attracted to and tend to recombine with positive ions at the first opportunity, thus again creating electrically neutral units. If an electron does not recombine with a positive ion, it can be taken out of circulation by temporary attachment to a neutral atom or molecule, which then has a negative charge until the electron is snatched away by the stronger attraction of some positive ion. Because of the strong recombination tendency, ionized gases will not remain in that condition unless there is a constant supply of energy to cause new ionization as fast as the previous ions can recombine. The first significant quantities of naturally occurring free electrons begin to show up at an altitude of approximately 60 kilometers, which we therefore consider as the bottom of the ionosphere. From there on up to heights of several hundred kilometers, free electrons become more and more prevalent. Their rate of increase with altitude is non-uniform, and there are several clearly defined regions which exhibit distinctive electromagnetic characteristics. The first region is the D region, frequently called the D layer, between 60 and 90 kilometers above the Earth. Centered at roughly 120 kilometers is the E region. At 200 kilometers, the F1 region. And finally, at some 300 kilometers, the F2 region. In the relatively dense atmosphere of the D region, there are sufficient numbers of diatomic positive ions that no free electron can exist for long without either combining with one of these ions or becoming attached to a neutral particle. There is no solar radiation to produce a resupply of new ions in the Earth's shadowed or night regions. However, cosmic radiation provides a source of ionization both during the day and at night. Nevertheless, the absence of solar radiation at night allows recombination to proceed more rapidly than ionization, and the free electron density is reduced compared to that during the day. Up in the F region, however, the extremely rarefied atmosphere allows a large free electron density to exist throughout the night. Shortly after sunrise of the following day, the D region ionization, consisting mostly of electrons, is reestablished by solar radiation. We are concentrating attention on atmospheric ionization processes because the free electron density at the various altitudes determines the signal propagation behavior of many of our radar and long-range communication systems. Now, in what way do high-altitude nuclear explosions affect these free electron densities? To begin with, roughly 70% of the total energy produced in a nuclear explosion is emitted in less than a microsecond as a flash of X radiation. A few percent more of the bomb energy is emitted as prompt gamma and neutron radiation. Most of the remaining energy appears as directed motion or kinetic energy of the expanding explosion debris. Delayed gamma and beta radiation from this radioactive debris material emits some 5% of the total weapon energy over a longer period of time. We will examine the effects on the atmosphere of nuclear detonations at 50 kilometers, 100 kilometers, and 250 kilometers altitude. First, let us consider the events that follow the detonation of a sub-megaton weapon at a moderate altitude of 40 to 50 kilometers. Most of the X-ray energy is deposited near the burst point, heating air to incandescence. The prompt gamma and neutron radiations from the explosion can, on the average, travel large distances before colliding with air particles. Therefore, the ionization caused by such collisions is spread out laterally over a region several hundred kilometers in diameter. Radiation in an upward direction increases the D-layer ionization, which we symbolize with the blue shading. It is important to realize that the greatest range of these radiations will be upward and horizontal, because the exponential nature of our atmosphere causes its density and absorbing qualities to decrease very rapidly in upward directions. Specifically, each 15 kilometers change in altitude in either direction will make about a 10-to-1 change in air density. At 45 kilometers altitude, the density is approximately 1,000th of the air density at sea level. Coming back to our explosion, the X-rays heat the surrounding air to incandescence. Within a tenth of a second, the tremendous radiant energy output and gas expansion processes have created a fireball of superheated air several kilometers in diameter. Inside the fireball, both the air and the smaller central mass of expanding weapon debris are fully dissociated from the molecular into the atomic state, and the atoms themselves are highly ionized. In another view, a high-velocity shock wave is seen to race outward from the radiation front, which is still at a temperature on the order of 10,000 degrees. The fireball expands at a slower rate to a diameter of 10 kilometers within about 5 seconds, during which time it also begins rising upward at a rate approaching 300 meters per second due to the buoyancy of its heated low-density gases. We watch the remainder of the explosion development through a camera located directly underneath the fireball. Sometime during the first minute, the rising cloud of fireball and debris material from explosions at this or lower altitudes interacts with the surrounding air, and the fireball transforms into a torus or donut shape. Both gammas and high-energy electrons or beta rays are continuously emitted from fission fragments in the debris. The cooling fireball and debris mixture, no longer luminous, continues to rise and expand, reaching a diameter of about 40 kilometers at 1 minute. It finally stabilizes some minutes later at an altitude of about 100 kilometers until dissipated by atmospheric winds. We will next consider a nuclear explosion of large yield at an altitude of 100 kilometers, where the atmosphere is less than 1,000th, as dense as it was at 50 kilometers. The initial heavily ionized X-ray fireball will be an order of magnitude larger than from our low-altitude shot, and much more tenuous and less brilliant in appearance, because so much of the X radiation escapes to large distances, over which it causes a significant ionization increase without luminosity. The atmosphere is so rarefied that the highly penetrating prompt gamma and neutron radiation from the explosion will produce only negligible concentrations of new ions in horizontal and upward directions. Ions are produced in the D layer and at lower altitudes. The hot and rapidly expanding fireball rises ballistically with something over 5 times the average velocity seen for the lower shot. Its diameter is some 300 kilometers after the first minute. Magnetic forces progressively distort the rising material, elongated along the geomagnetic field lines. Maximum altitude on the order of 1,000 kilometers is reached in 7 or 8 minutes. With the upward ballistic impulse exhausted, the material, being heavier than the ambient atmosphere, tends to fall back to denser regions on the order of 150 to 200 kilometers. The fall is oriented primarily along the Earth's geomagnetic field lines. The diameter is several hundred kilometers with a thickness perhaps a tenth as great. The diffuse radioactive debris continues emitting both gamma and beta radiation with significant intensity for many hours after the explosion, thereby continuing to produce ionization. Most of the ionization from gamma radiation occurs at altitudes near 30 kilometers. However, ion lifetimes are very short down in such relatively dense air. Reattachment is so rapid that we actually find the greatest net population of gamma-produced free electrons up at the D-layer altitudes, where the reattachment rate is much lower. The other major radiation from the debris, the super high-velocity electrons from fission fragment decay, referred to as betas, are less penetrating than the gamma rays. Most of the downward-directed betas dissipate their energies in the D region at 60 to 80 kilometers, adding to total ionization in that region primarily by collision with neutral particles. The area of the ionization region created by beta radiation will correspond roughly in size to the area of the stabilized debris material itself. Actually, being electrically charged, the beta particles are constrained to follow the Earth's geomagnetic field lines. Thus, a region of ionization commonly called the beta patch is caused by these downward traveling electrons. The few beta particles that start out parallel to the field line will continue to follow them. If the particles encounter the field lines at an angle, however, they will spiral around them. Here we see beta particles streaming along the magnetic field through the fireball and debris of a burst. Those electrons ejected upward may be trapped along the Earth's magnetic field lines and are mirrored back and forth if the reversal or mirror point is substantially clear of the atmosphere. If the mirror points are too low, the electron will dip into the atmosphere at each end of its shuttle and soon will be lost by collision with air molecules. This collision excitation mechanism is generally accepted as one of the causes of auroral displays. Thus, a nuclear burst at sufficiently high altitudes can produce auroras at conjugate points in both hemispheres. Since the debris from a nuclear detonation begins radiating at the moment of the explosion, its conjugate point auroral effects can be expected to change location as the debris rises and intersects with successively higher magnetic field lines. Note that when the debris is located below about 200 kilometers, most of the electrons shuttling along the field lines will be lost in the atmosphere on their first pass, with very little mirroring back to the other conjugate point. We will next consider a nuclear explosion at altitudes above 250 kilometers. Mass asymmetries in the construction of the nuclear device and its carrier can be very important and are observable in this 400-kilometer explosion. At this very high altitude, a substantial change occurs in the mechanism of containment, the forces which slow and finally stop fireball and debris expansion. While ordinary hydrodynamic pressure resists the explosion expansion at low altitudes, geomagnetic back pressure becomes increasingly important at altitudes above 100 kilometers. The heavily ionized debris and gases in an expanding fireball are electrically conductive, so the Earth's magnetic field tends to be excluded from that region, creating a so-called magnetic bubble, which presses back against the expanding gases. At great altitudes where air pressure is negligible, expansion might continue indefinitely if it were not for a collisionless process in the debris and surrounding air plasmas, which permits a degree of coupling between the weapon debris and the ambient atmosphere. The degree and nature of the coupling are believed to be very dependent on yield and burst altitude, but these processes remain major unknowns in the phenomenology of very high altitude nuclear explosions. Looking back again at another weapon effect on the atmosphere, most of the prompt gamma radiation is deposited between 25 and 30 kilometers altitude. The air molecules are ionized, and the free electrons split off and start spiraling around the magnetic field lines. Each spiraling electron emits minute radio waves. All of the electrons exist nearly simultaneously, and the minute radio waves add together. This is the primary source of the high-altitude electromagnetic pulse, or EMP, which is a broadband pulse of radio frequency energy radiated from the deposition region. When this electromagnetic pulse is coupled into a system, very large voltages and currents may be induced. Other EMP generating mechanisms are operative in other burst regimes, but are outside the scope of this film and will not be described. In brief summary of the important effects on the ionosphere, we see that a nuclear burst in the 40 to 50 kilometer region produces first a heavily ionized fireball area, while the flash of prompt gamma and neutron radiation causes significant ionization lasting for several minutes and extending to large distances horizontally and upward, but with only minor range and duration in downward directions. Debris radiation continues to create intense ionization in the region of the fireball while it rises. At all explosion altitudes substantially above 50 kilometers, the immediate radiation produces almost completely ionized fireball regions of multi-kilometer dimension. Its strong but radially decreasing ionization extends to many hundred kilometers. The fireball and debris materials rise to maximum heights of from 100 to 1,000 kilometers as the burst height is raised from 50 kilometers to the 100-kilometer region. Unlike debris from the lower explosions, material from the higher explosions falls back from its maximum altitude, ultimately settling around 200 kilometers. With rising burst altitude, greater quantities of beta particles and charged debris particles will shuttle north and south along the magnetic field lines to conjugate points in both hemispheres. Both beta ray and debris interaction with the atmosphere at those points will, for a number of hours, create significant ionization with vivid auroral effects and radio disturbances. Debris gamma and beta radiation will also enhance ionization in the D region at both conjugate points. Other phenomena associated with irregular structure in nuclear burst ionized regions are also important to communications, infrared, and radar systems. One is the eventual development of magnetic field-aligned filaments, or stria, in ionized regions. Irregular ionized structure also results from the upwelling or heave of explosion-heated air above 100 kilometers altitude. These phenomena are treated in greater detail in Part 2 of this film, which considers the effects of atmospheric ionization on military systems.